Today we're going to be looking at logarithms and logarithmic functions. And I want to start just by explaining what a logarithm is and why we need it. So as we saw yesterday, we're able to solve some exponential equations. So if we had something like 4 to the power 2x equals 16 to the third power. What we saw yesterday, if we could rewrite both sides having the same base, then we can use the equality property of exponents to solve this equation. So if I can rewrite 16 as 4 squared to the third power and then multiply my exponents, well then we know that since both sides have the same base, that the exponents must be equal. 2x must equal 6, so x would equal 3. But there are some other types of exponential equations that we're not able to solve that way. So if I have the exponential equation 4 to the x power equals 50, for example, well, I'm not going to be able to use the equality property of exponents here. There's no way I could rewrite 50 as having the same base as 4. So we need a different strategy for exponential equations like this. In the early 1600s, a guy named John Napier came up with the answer. He developed a new type of function called a logarithmic function, which he said is just the inverse of an exponential function. So if you had an exponential expression like y equals b to the x, you could rewrite that in logarithmic form, where you can take this x and say that is equal to the log with the base b, the same base that the exponent had, of y, the number it was equal to. So you're essentially asking what exponent of b, the base, equals that number. So if we had that same equation from the last slide, 4 to the x power equals 50, the way we could change that to logarithmic form is by saying x, the exponent, equals the log with the base of 4, because it's the same as the base of the exponent, of this number we're trying to get it to equal, 50. So this would be this expression written in logarithmic form, and it's a way to get x by itself. So let's just practice taking some exponential expressions and writing them in logarithmic form. It takes a little practice, but once you get the hang of it, it's pretty easy. So our first one, 10 to the third power equals 1,000. So if I want to write this in logarithmic form, the pattern is going to be exponent equals log with the base of the number. So if we can follow this pattern on all these, it'll be pretty easy. So the exponent, 3, equals the log with the base, what's the base here? It's 10, of the number. So 3 equals log base 10 of 1,000. If we try the next one, 9 to the 1/2 power equals 3, we can follow that same pattern. The exponent, 1/2, equals the log base 9 is the base of the exponent here, of 3. And if we look at one more, 5 to the third power equals 125. We'll follow the same pattern. Exponent, 3, equals log with a base that's the same as the base of the exponent, 5, of 125. So that's just how we can rewrite an exponential expression in logarithmic form. It's the same thing, it's the same equation, just written in a different form. Well, we can also do this the other way. We can take a logarithmic expression and write it in exponential form. It's going to follow that same pattern of exponent equals log with a base of the number. So whatever is the base of the log is the base of the exponent. So this first one, log base 8 of 1 equals 0. Well, 8 is the base of the logarithm. It's also going to be the base of the exponent. The number by itself on the other side is the exponent, and the number we're taking the log of is the other side of the equation. So we end up with the equation 8 to the 0 equals 1, which is a true equation. Anything to the 0 power does equal 1. Let's try it again here. Log base 2 of 1/16 equals -4. Well, 2 is the base of the logarithm. That's going to be the base of the exponent. The number by itself over here is the exponent, so 2 to the -4th power, and that's going to equal 1/16. And again, we can see that that equation really is true. This last one, log base 3 of 9 equals 2. We could write that as 3 squared equals 9. Again, it's the same way of writing the same equation, just in exponential form instead of logarithmic form. So the types of problems you'll see on your assignment today will say evaluate a logarithm. And it'll give you something like this, the log base 2 of 64. So the thing we need to be asking ourselves when we see this type of problem, this is really asking us the base to what power equals that number. So if I see something like log base 2 of 64, what this is really asking is this base 2 to what power would equal 64. So we have to go through our powers of 2. 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, 2 to the 5th is 32, so 2 to the 6th power would be 64. So then when we evaluate this, the log base 2 of 64 would equal 6, because that is the exponent of 2 that equals 64. We do the same thing here on this other example, the log base 3 of 243. What this is really asking is 3 to what power equals 243. So again, we might need to know some powers of 3. 3 squared is 9, 3 cubed is 27, 3 to the 4th is 81, and if we just triple it one more time, 3 to the 5th would be 243. So this would be equal to 5, because 5 is the exponent we're looking for. And then we'll finish off today with just a couple interesting properties of logarithms. So if we see something like the log base 6 of 6 to the 8th power. So if we have an exponential expression here in the logarithm, that might make it look more complicated, but really it's pretty simple. What this is really asking is 6 to what power equals 6 to the 8th power? Well, that's pretty easy to figure out when you think of it that way. 6 to what power equals 6 to the 8th power? Well, 6 to the 8th power. So this would be equal to 8. Remember, when we're doing a log, we're always trying to solve for an exponent. So if I have something like the log base 9 of 9 squared, then that's just going to equal 2, because we're always trying to figure out that exponent. So what this is showing is that a logarithm with a base of 9 is the inverse of an exponent with a base of 9. Anytime we see a logarithm and an exponent with the same base, those basically just cancel each other out and leave us with just the exponent. The same thing happened here. The log had a base of 6, the exponent had a base of 6. Those canceled out. We're left with just 8. It also works the other way around. In this problem, I have an exponential expression with a base of 3, and then the exponent is a log with a base of 3. Well, anytime we see an exponent and a log with the same base, those are just going to cancel each other out. So this expression that looked kind of complicated, 3 to the power log base 3 of 4x minus 1, well, that's just going to simplify to 4x minus 1, because the exponent and the log had the same base. And if we look at just one more example, if I have another one similar to that, 7 to the power log base 7 of x squared minus 1, well, since we have an exponent with a base of 7 and a log with a base of 7, those are just going to cancel each other out. And this is equal to x squared minus 1. So in the next couple of days, we're going to start using logarithms to solve more types of exponential equations. But for today, I just want you to get a little practice working with logarithms and evaluating them like we did here on the last couple slides. Please let me know if you have any questions, and I hope you have